So let's continue with our gradual proof of universality theorem. Again, we'll go step by step, building up on what we have built so far. So this is the statement. We're constructing a universal program, u sub n, that computes this function, right, phi of n, x1 through xn plus 1, or f phi n x1 through xn y, where x1 through xn are arguments to the program whose number is y. So let's review what we have built so far. We have extracted the source code. Z is the source code, and it is obtained by adding 1 to the value of xn plus 1. S is a Gödel number that encodes the state of the program. So essentially, every even prime is raised to every prime in an even place. So the second prime, the fourth prime, and so forth. So this is what p sub to I. And it encodes this, the value of the specific variable. So x1, x2, x3, and so forth. So then k is the instruction counter. It is set to 1, and then u is the function r applied to z sub k, and z sub k is the kth instruction. So the instruction, recall, it's a pair of numbers, right? The first element is the label, and then let me review this here. So the instruction is compiled, so it's equal to z sub k. So let's cross our z's just to be uniform. I is which is z sub k, and it's a pair, so encoded with our pairing function. It's a pair whose first element is a number and whose second element is also a pair. Well, it's also a natural number. So so u is equal to r z sub k equals to b c, the pair of bc, and then l of u equals to b, right? So that's the instruction type. So if L of u, the instruction type, is equal to 1, then we go to A, right? This is the label that we use for addition, right? Of course, technically speaking, L does not allow for labels such as A, but we can rename it into L1, L2, whatever. So this is just to make sure that this information is available. This is the label. This is the instruction type. So addition, no-op, multiplication, and minus, and conditional dispatch. Okay, so and C is the variable number, and this is the prime corresponding to the variable, right, that encodes the value of the variable number C. So this, if p to the v divides s is a Gödel number, then v is the value of s sub ru plus 1. Okay, because c is actually the variable number minus 1. This is how the Gödel compiler or the Gödel coder encodes instructions or compiles them. So, and we covered that information in the previous screencasts. So if L of u is equal to 0, then we do nothing. N is the label, can be thought of as the label for nothing. And I'm using double forward slashes as comments. So it's like in Java or C++. Why we do nothing? Because if b is 0, L of u is 0, then the instruction is a no-op. V goes to v. Now, if p does not divide s, then we also do nothing, right? So let's continue here. on the whiteboard. If it is not the case that P divides S, then we go to N. Why? Because we've already taken care of addition, and we are about to start taking care of minus, right? And if the value of the variable used in the instruction is 0, then there's no need for us to subtract 1 from the value of v, because we're not allowed to go negative, right? The values of the variable, since we're in the domain of natural numbers, must remain 0 or positive. So, and if the prime, so some p to the I, right, does not divide S, that means that the ith element of the prime is 0. And if it does divide S, then the ith element, the value of the ith variable, is not 0. So if L of u is equal to 2, that means that we have to do minus. So we will dispatch to M minus. Okay. Now, so what happens if L of u is greater than 2? If L of u is greater than 2, that means that we have a conditional statement, and we have to dispatch to the appropriate label. Right? If L of u does equal to 2 and P does divide S, because we've already taken care of the case if P does not divide S. So if that means that if L of u is greater than 2 and P does divide S, I is of the form if V is not equal to 0, then go to L, right? Okay. So, and the number of label L, right, is equal to L of u minus 2. Okay. So because the compiler, the Gödel compiler, actually adds 2 to the number of the label, so we have to subtract 2. So if B L of u is equal to 2, that value is put into the pair by the Gödel compiler. So we need to look for the smallest instruction number, I, or the smallest line in our program, the smallest I, such that z sub I, instruction number I, is of the form, okay, A sub I, then B sub I, and then C sub I, right? Okay. And A sub I is equal to B minus 2, and B is equal to L of u plus 2, right? So since A sub I, well, so that's what we should be looking for. So we will set the instruction counter to the value of the bounded minimalization. Starts from 0, and we'll go to the length of the program. Z is the source code. So you can review the screencast on the length of natural numbers on this channel. So we're looking for L of z sub I. So in other words, the A of z sub I plus 2 is equal to L of u. So k is 0, right? This is by the definition of the bounded minimalization. If there is no such label, and there may not be such label, then minimalization is unsuccessful and k is set to 0. And that is the only case when k can be set to 0. And then we go back to the label C, computation label or continue label. Okay, so let's recap what we have constructed so far. So U sub n, this is our universal program, right? Okay, and the construction we follow Davis, Weyuker, and Segal, computability, complexity, and languages, right? It is their construction. So this is the source code. This is the state of the program, encoded as a Gödel number. This is the instruction counter. And this is our continue label or computation label. So we check if we are one past the length of the program or k is equal to 0. In either case, we go to E, exit. Right? K can be set so if k is equal to the length of the program plus 1, then the program has terminated successfully, and if k is equal to 0, that means that we have failed to find a label mentioned in some instruction. So this is our B and C component, the instruction type and the variable number used in the instruction of the current instruction, number k. So and this is the a variable. Okay. So the variable number, well, it's actually technically -1, so we'll have to add 1 to it. So this is the prime, ru plus first prime. We need that prime to get the value of the variable from the Gödel number. So we'll have to add 1, right? Because the compiler actually subtracts 1. So if L of u is equal to 0, the instruction of type v arrow v, it's a no-op. If L of u is equal to 1, then we go to addition. If p does not divide it, that means the value of the variable is 0, so we do nothing, right? Because we cannot subtract. Okay, if L of u is 2, then we go to minus, and otherwise we look for the label, take care of the conditional dispatch, and then we go back to C. Okay, check for the continuation condition and either continue or exit. So this is the conditional dispatch. File of u must be equal to b greater than 2. So I have the instruction of the form if v is not equal to 0, go to L. Okay, this is to be continued.